Hello everyone. We have seen some discussion related to thermal sensing. So, we are almost towards the end of thermal sensing discussion. So far we have seen how the dynamic characteristics associated with thermal sensing will influence the response. We also have seen how object temperature and sensor temperature is related to each other, and finally we kind of concluded that even in dynamic condition or in static condition, it is very difficult that the sensor temperature will ever reach to the object temperature. So, it is very difficult that the sensor temperature will be equal to the object temperature. As far as the thermal resistance is concerned, we already have discussed that for an efficient performance of a temperature sensor or a thermal sensor, it is very important that the thermal coupling between the sensor and the object is very good, and the thermal coupling between the sensor and the environment is poor. So, today we will also check what are the different temperature sensors that are available. I mean, broadly speaking, we can classify them as contact sensor, where the sensor comes in contact with a object, or the sensor material to some extent is kind of getting in touch or come in contact with the object itself. In that case, you have a sensing element and then there is an envelope which protects the sensing element, and then the entire sensor can come in contact with the object while measuring the temperature. It has two terminals. These two terminals are used to take the electrical output from the sensor. Then there is another type of sensor which is known as non-contact sensor, where you have a housing that covers the sensing element present inside, and then the sensor interacts with the external object through a window. So, we call it non-contact sensor. So, in that case, the sensing element is actually not coming in contact with the object. So, the sensing element takes the heat response through this window, and there is an housing associated with that, and then it also has terminals, so that we can take the electrical response from the sensor itself. So, the basic phenomena associated with temperature sensing is that your electrical resistance is a function of temperature. If it is a thermistor, then your electrical resistance of that particular material is a function of temperature. So, it is like R is equal to temperature, function of temperature. That is what usually is the case. Now, Sir Humphrey Davy in 1821 first observed this type of behavior for metals in 1821. So, it is like an observation long before in 1821. Then in 1871, Sir William Siemens used platinum resistance thermometer for temperature sensing application. So, the temperature sensing concept is not something that is very new. The idea behind putting these two information, that in 1821 and 1871 people have, in fact in 1821 somebody have seen similar response, that there is a relation between temperature and electrical resistance in metal, and then somebody took platinum resistance thermometer or made a platinum resistance thermometer in 1871 for certain applications. So, it is not something very new, that was there for a long time, but with time things are evolved in order to make those sensors more applicable or more sensitive. In that respect, that thermoresistive sensors can be divided in three different subcategories. The first one is resistance temperature detectors, also known as RTDs, and RTDs can be of two types, thin film based and wear round type. Okay. So, in both the cases it is a resistance temperature detector that detects the temperature based on the change in resistance. Then we have PN junction detectors, which is again from the name itself it is very clear, which is based on a PN junction, semiconducting PN junction. Then we have thermistors, widely used in different applications, and thermistors are again based on electrical resistance, that is, or that changes in response to the applied temperature. Now, in that respect, the sensor can be PTC or NTC, that is positive thermal coefficient, negative thermal coefficient. That means when you increase the temperature, the resistance can either increase, that is positive thermal coefficient, or with the increase in temperature, the resistance may decrease, that is negative thermal coefficient. So, here two plots are given, schematic plots are given to make NTC and PTC, to represent NTC, response of NTC and PTC. So, in this case, if you increase the temperature, the resistance is increasing, and then in this case, when you increase the temperature, the resistance is decreasing. So, in this case it is NTC, in this case it is PTC. For RTDs, mostly they are PTC, that is positive thermal coefficient. It has positive thermal coefficient. If you increase the temperature, the resistance will increase. But in case of PN junction detectors and thermistors, this can be both NTC and PTC. So, it depends on the material, whether the material resistance increases with temperature or the material resistance decreases with temperature. Now, based on experimental study, thermistors resistance S and absolute temperature T can be related using or by a polynomial equation. So, usually when someone model the temperature sensing response, then they take a polynomial equation which is given over here. So, it is like ln into s, or not ln into s, it is like ln s is equal to a0 plus a1 divided by t plus a2 divided by t square plus a cube divided by a3 divided by t cube, and so on and so forth. Now, from this equation, many have modeled a temperature sensor, and you will find those models in literature as well. And for a narrow temperature range, if your temperature range is not very high, and if you can compromise the accuracy to some extent, then the equation can be reduced to ln s is equal to a0 plus a1 by t. So, you just take the first two terms. Anyways, if your temperature value is quite high, then t square t cube terms will not be that significant. So, you can reduce the higher order terms anyway. So, in this case, your equation will be reduced to ln s is equal to or approximately equal to a plus beta m by t. Beta m is a material characteristics, and a is a constant. Okay. Now, these values one can calculate from different initial conditions, but the idea is, if your value of t is very high, or if you are working with a narrow temperature range, and if it is okay to compromise the accuracy to some extent, you can get rid of the higher order terms, or you can just neglect the higher order terms to keep things simpler. That is the idea. Now, if you take this particular equation, then your response S is equal to e to the power a plus beta m by t. Now, again, if you do not know what is the value of a, the constant value, you take an initial condition, say for t equal to t0, when your temperature is equal to t0, your response is equal to S0. That you may figure out using a experimental study, and then if you put it in this equation, then your S0 is equal to e to the power a into e to the power beta m by t0, then your e to the power a term becomes S0 into e to the power minus beta m by t0. Then if you put the value of e to the power a in equation 2, then your S is equal to e to the power a into e to the power beta m by t. So, S0 into e to the power minus beta m by t0 into e to the power beta m by t. So, it will give you this equation, that is the relation between response and the temperature, where S0 is known, T0 is known, beta m is known because it's a material property. So you will very easily can find out what is the response of the sensor for a particular temperature. So this is one way of doing it. And then, for example, say you also do not know what is the value of beta m, which is a material property. So in that case, you take a 2-point calibration, that is one condition you already know, that at t equal to t0 your response is S0. Then you also figure out at t1 what is your response. Put both the values in equation 3, then you will get from equation 3 you will get that ln S1 by S0 is equal to beta m 1 by T1 minus 1 by T0, and then from there you will get the value of beta m, because now you know the value of S0, the value of S1. Put this one in equation 3, you will have S0 equal to something. Put this value into equation 3, you know what is the value of S1, and then you take the both the equations and you can figure out what is the value of beta m, which is nothing but ln S1 by S0 divided by 1 by T1 minus 1 by T0. Put this value of beta m into the equation 3 again here, and then you will find the value of T is nothing but 1 by T0 plus ln S by S0 into beta m. So here also you will get an, it should be to the power minus 1, okay, so it is not here. So if you do these rearrangements, then you will find the relation between T and S. So the idea of showing this particular equation is to give you an example of temperature sensor modeling, simple modeling. So you can take a polynomial equation, maybe in different literature also you may find that people have taken different polynomial equations, and then they have come up with different equations that can very easily model or mimic the temperature sensor response. So here different types of temperature sensors are shown. So right from thermocouple, RTD, thermistor, semiconductor based temperature sensor, liquid thermometer, all these types of some temperature sensors are shown over here. So these are the different classification of temperature sensor to some extent, where you can find that the working principle is bit different from each other, but ultimately the target or the objective of all these devices are to convert the temperature into an electrical signal which we can measure or process later. So the basic working we already have seen in the previous slides or previous lectures, but uh, when it comes to a specific working, then one has to also look into different other parameters associated with it. One of the most common or commonly used temperature sensor is thermocouple and thermistor. So in case of thermistor, you'll find that there is a active material which is present and encapsulated by a layer, so that the active material is not getting affected by the environmental parameters, and there are two terminals which is made of metal wares. So most of the cases these thermistors are temperature sensitive. I mean, the resistance of these thermistors are temperature sensitive. We also have discussed in the classification, if it is an NTC thermistor, then the resistance will decrease with the increase in temperature, and if it is an PTC, then the resistance will increase with the increase in temperature. So both types are useful, and you will find the use of both these types of thermistors in various fields. And then you have RTDs, you have thermopile, you have thermocouple, and then semiconductor based temperature sensors as well. In this case also, in fact, you may use a semiconductor material for thermistor type of application. What I mean by that is you can use a semiconductor material for uh, or as an active material of a thermistor, because ultimately the thermistor's working principle is with temperature the resistance should vary. In case of semiconductor material, we see that if you increase the temperature, the resistance of that material will change. That is how usually the semiconductors behave. So in that case, you can actually use a semiconductor material as an active material of a thermistor. That is also possible. And then you also find some sort of device based temperature sensor. For example, say LM35 is a temperature sensor which has three terminals, and this is kind of a device based temperature sensor. And apart from that also, you may find different other device based temperature sensor where MOSFETs or BJTs are used in order to detect temperature. And here you can see a temperature sensor which is actually not electronic. It's based on the expansion of a liquid present over here, which is mercury. So if you increase the temperature of this region, the mercury present in this chamber will start rising because it expands when you increase the temperature, and based on its expansion you'll be able to find what is the temperature, because in the scale here the temperature is written. And if you see the expansion and then if it reaches up to here, then what temperature is written over here should be the temperature of that object. So this is a normal thermometer we usually use for to measure our body temperature. This is a liquid thermometer. This is also a temperature sensor, but the working is completely different. In that case, in this case at least, you don't have any electrical output. It's like visual identification of the temperatures based on this temperature sensor device. Okay, so that's why I said maybe in the beginning that it is not mandatory that when you have a transduction or kind of sensing, it's always electronic in nature. There are sensing which is actually not electronic. For example, in this case, this is a very good example of that, where you don't have an output which is electrical in nature or electronic in nature. So this is also a temperature sensor, but it's not electronic. But others present or shown over here is kind of an electronic temperature sensor, and that these are the typical images of different types of temperature sensor so that you can get an idea. And another temperature sensor is LM35, which is not shown over here, but that is also a kind of temperature sensor which is sort of device based. So that is this particular slide I've shown you just to give you an idea that how these temperature sensors look in practice. And you can use these temperature sensors for various other applications. So three take home messages from this discussion is temperature sensor can be of various types. We have seen that it can be contact sensor, it can be non-contact sensor. So contact sensors are the sensors that come in contact with the object in order to detect the temperature. Non-contact sensors are a sensor which interact with the external environment through a window. It is usually kept inside a housing. So the idea of keeping a housing is to protect that sensing element from the external environment, and it depends what are the materials that you are using for development of these sensors. And then again we have seen that sensors can be classified in terms of whether it's RTDs, whether it's PN junction based, whether it's thermistors. So the sensors can be classified in various ways, and one should know which sensor is applicable for what application. So again, this depends on the specification of the sensor. So one should know what are the specifications, what is the range, sensitivity, that we already have discussed while we discussed the sensor parameters to some extent. And the second thing that is like temperature sensor response can be modeled. As we have seen, these are two simple models, but people probably used previously. There are more complex models as well. These are not the only one. This is just to give you an idea that temperature sensor response can be modeled mathematically, and mathematical modeling is very important because in that case you can actually program the temperature or program a microcontroller to get a better response from a temperature sensor, so on and so forth. And then temperature sensor can be of contact and non-contact types, that I already have said. It's kind of a classification also, and based on application you have to choose whether to use contact sensor or non-contact sensor. With this, I would also request you to study or to think what is the difference between NTC and PTC, and is there any specific application you may think of where NTC will be more suitable than PTC or vice versa. Because you have options, you have both NTC sensor and PTC sensor. NTC sensor is a sensor having negative thermal coefficient. That means the response of the sensor decreases with temperature. PTC is the sensor where the response increases with temperature. Now, if you have both NTC and PTC sensor with you, on what basis you will decide for a particular application we should use NTC or we should use PTC? So you may think about this. It's not very difficult again, but I want you to think, and in the upcoming discussion we will start different aspects of chemical sensing, and we will try to figure out what are the different conditions associated with chemical sensing. Thank you very much.